So let's look at another example where we'll use iterated integrals in polar coordinates. In this example, they've just described the region over which we want to integrate and given us the function we want to integrate. We have to figure out what this region looks like. So I'll draw my XY coordinate plane because my region is described in terms of X and Y coordinates here. I'm told that x squared plus y squared is greater than or equal to 1. So the circle of radius 1 is x squared plus y squared equals 1. I'm greater than or equal to that. And x squared plus y squared is less than or equal to 4. So the circle of radius 2 is given by the equation x squared plus y squared equals 4. So I'm in between the two. But I also am told that y is between 0 and x. So the line y equals x y is between 0 and that. So the region that it's describing is here. Between the two circles, and y is running from 0 to x. So again, that looks like a nice region that we can describe in terms of polar coordinates. We also need to know how to translate the function 9 times arctangent of y over x in terms of polar coordinates. So let's remember our substitutions. X equals r cosine theta. Y equals r sine theta. So y divided by x is r sine of theta divided by r cosine of theta. Well, r and r cancels. I have sine of theta over cosine of theta, which is tangent of theta. So I have y over x is equal to tangent of theta. If I take inverse tangent on both sides, I have arctan y over x. And because I know that my angle is between 0 and pi over 4, and my arctan gives me back angles between negative pi over 2 and pi over 2, then I get to say this is just theta. I don't have to make any other adjustment. So I have arctangent of y over x is equal to theta. So 9 arctangent of y over x is 9 theta. Great. So now I think I have all the information I need to set up this integral. I'm going to say integration. My theta bounds are between 0 and pi over 4, according to the picture, because my y runs from 0 to the line y equals x. My r bounds are from 1 to 2, because I'm in this annular region between the circle of radius 1 and the circle of radius 2. The function that I'm integrating is 9 theta, because I switched 9 arctangent of y over x by 9 theta. And this is r dr d theta, where the r comes from my Jacobian. So I'll integrate with respect to r first. I have 0 to pi over 4, 9 theta r squared over 2 from 1 to 2. Then taking the antiderivative in terms of theta later. So 2 squared is 4. I can say this is 0 to pi over 4 times 9 times 4 over 2. I think I want to pull the 9 over 2 out. So I'm going to say 4 theta and minus 1 theta. when I plug in 1. Because I pulled 9 over 2 out, I just have 1 squared. That's theta. So of course, it's 3 theta, so I get to say this is 27 over 2 outside, 0 to pi over 4, theta d theta. And the antiderivative of theta is, of course, theta squared over 2. So this is 27 over 2, theta squared over 2, evaluated between 0 and pi over 4. Clearly, when I plug in 0, I'm going to get 0. So this is just 27 over 2. Let's go ahead and pull out the other 2. 27 over 4 times pi squared over 16. If I've squared pi over 4, so I get 27 pi squared over 64. So again, I was given the region in x and y coordinates. I translated it into polar coordinates, and a function as complicated as 9 arctangent of y over x became as simple as 9 theta.